This video will be on the derivation of Euler's formula, which will allow us to understand complex numbers in terms of their polar form. First, we will look at how we can write a complex number in terms of cosine and sine. So I'll build a complex plane. Now let me add a unit circle. And I'm also going to include an arrow which initially points at 1. I want to point out that the length of this arrow is 1. And even if we rotate the arrow, even though it no longer points to the number 1, the length, like if you put a ruler up here, it would still give us 1. Now let's rotate it by some angle. And let me call this angle t. And I'm going to introduce a function called p of t, which just gives us the complex number we have as we vary t. For example, p of 0 would be 1, p of pi over 2 would be I, if we're thinking in terms of radians. We want to come up with an expression for p of t. Now I'm going to point out that we can build a right triangle just like this. So in here, if you look here, we have a right triangle. Now the length of this side, if I put the ruler up here, the length is just 1. We started with this arrow of length 1 and we rotated it, it didn't change the length. And then from trigonometry, we can get these lengths. This side has length, cosine of t. And this side has length. It has length now. This isn't the actual complex number, but it has length, sine of t. So the way we get to p of t is that we walk over cosine t in the real direction, and then in the imaginary direction, we walk a distance sine of t. So this is what we get. We get p of t is equal to cosine of t plus, now we need to walk a distance sine of t in the imaginary direction, so the way we write that is I times sine of t. We're now going to derive a different expression for our function p of t. We'll again build our complex plane and our unit circle. And let's go ahead and include our arrow. But now I want you to think of the arrow as representing the position of some person walking around the circle. As this person walks around, I want you to think about their speed. What direction is it in, and could you describe it with an arrow? So let's do it again, but now I'll include an arrow representing their speed. So this arrow, right here, is representing the person's speed as they travel around the circle. And let me erase this. Now I'll include some labels here. So we have t, and this arrow is p of t. Now I want us to think back to calculus. If p of t represents the position of the person, then their speed is given by the derivative, in essence p prime of t. Which means that this arrow, the arrow representing the speed, is actually p prime of t. Now I want to point out that there's a 90-degree angle between these two arrows. And it looks like if you take p of t and you rotate it 90 degrees, what you would end up with is p prime of t. So let me write that out explicitly. P prime of t is equal to p of t, not just p of t, but p of t rotated 90 degrees. I want you to think about this equation. What does this say about p prime of t? Thinking about this equation, p prime of t is equal to p of t rotated 90 degrees, leads us to the following question. How do we rotate numbers (90 degrees)? Well, this is precisely how we introduce the imaginary number I. So we end up with the following equation. P prime of t, well, from before it's supposed to be equal to P of t rotated 90 degrees, but that's what I is going to do. So it's equal to I times P of t. This is called a differential equation, and in a later video I'll show you how to solve it, but for now you just have to trust me that the solution is this. P of t is equal to e to the I t. So now we have a new expression for P of t, and combining it with the old expression gives us this. P of t, what we just derived is e to the it, and from before we have cosine of t plus I sine t. Let me box this around. This is called Eulers Formula. I think this is a good place to end this video. We'll learn how to apply Euler's formula more extensively in later videos.